to speak at the special occasion. Today I'll talk about something relates to the four-dimensional Ricci flow and the singularity formation. Before I start the talk, I'd like to particularly thank Professor Yao again, because that's 42 years ago, exactly in spring, when Richard Hamilton came to Princeton Institute for Advanced Study, visiting Professor Yao, and presented his new work of Ricci flow on three manifolds. And immediately after Hamilton left, Professor Yao asked all his three first-year PhD students, Bendo, Ben Chao, and myself, to start learning Hamilton's paper. And since then, it has more than 40 years, and I still receive the advice and encouragement from Professor Yao. And today, what I talk about actually is related to a trip that I visited Professor Yao 15 years ago about, and he specifically just mentioned focus on four manifolds. And so I'm going to talk about something related to four manifolds. Okay. Now, as many of you all know, one very special feature of four manifolds differential geometry is this decomposition of two forms that into self-dual and anti-self-dual two forms. So, of course, it's also related to the algebra. SO4 is the direct sum of two copies of SO3. And correspondingly, so the decomposition, you have the curvature operator, which is acting on the from two form to two form, self-adjoint bilinear form, if you want. So in this case, you have the corresponding decomposition block, matrix block decomposition of the curvature tensor into four pieces. And so A is the so-called self-dual via part, and the plus the scalar curvature, and then the B part is traceless, essentially related to traceless Ricci tensor. And then you have also W minus, so the self-dual and self-dual via tensors, the scalar curvature. So this is well known for four manifolds. And in this special case, the so-called notion of positive isotropic curvature, PIC, is very simply expressed as the both A and the C matrix are two positive definite. And so also remind you by the first Bianchi identity, the trace of matrix A equal to the trace of matrix C, which is essentially given by scalar curvature. Now, because of course the PI notion is valid for all dimensions bigger than or equal to 4, but in the special case of the 4 dimension, we also can have a notion called a half PIC. So that means either A or C is two positive definite. And similarly, we can also weakly positive definite non-negative. So you got A and C are weakly two positive. So you get half W PIC or the W PIC. All right. So examples, the standard examples are the S4, S3 cross R are the two examples which are PIC. And so the A matrix, of course, in this case, S4 is Einstein for sure, a constant space section of curvature space forms. You got is the least eigenvalues of these are exactly 0, and so these are the standard examples. Now, relation between various, of course, we got the classical concept. The sectional curvature is positive. That's K, denotes K positive, that's sectional curvature. And when that's the Pick notation was introduced in 1988 by McCullough and Moore, and they also observed that both curvature operator positive or quarter pinching implies the complex sectional curvature is positive, and that implies the sectional curvature is positive. And so this is so-called a pick two and pick one. And by pick two, pick one means you what's going on here? Oh, I think I pushed the wrong button. So the pick one means the manifold cross the real line is pick, and pick two is manifold cross the plane R2 as pick. So for the cross the real line is pick, and pick two is manifold cross the plane R2 as pick. So in the sense that the pick condition only implies the scalar curvature is positive. So but if you have pick one, that implies Ricci curvature positive, then pick two implies sectional curvature is positive. And that's the relation between various notions. Now, so what as Professor Yao reminded me that Taub's JDG 1992 JDG paper, that the Taub's results says any compact oriented four manifold without boundaries closed. So if you connected some enough copies of CP2 bar, then you can make it half conformally flat. That means the W plus is equal to 0. So that's anti-self dual. And that also that inspired Hamilton to make the following proposals. It has two parts. The first part is use the Ricci flow to classify compact four manifolds with half pick. I'll talk about why not pick, but pick so half pick. So half pick, of course, already implies positive scalar curvature, and especially investing singularity formations under the half pick condition. The second part is hopefully use the Ricci flow to approach the so-called stable classification of compact four manifold with positive scalar curvature. And that means if you can, by connecting some of many copies of CP2 and make them, say, have half pick. That's still the ask expert whether that's possible, because we all know connected sums preserve the scale curvature positivity, right? But also half conformally flat, that is also preserved under conformal. So hopefully this can be done. If that's the case, then we have start for any compact four manifold with positive scalar curvature. We can make it half pick by connecting a large number of copies of CP2 bar, and then hopefully with a Ricci flow and see what happens. Now, this Hamilton's proposal certainly is comes from the result. So let me first talk about topological implications. These are well known for compact manifolds in general. So McCullough and Moore, they proved if it's compact simply connected, then the pick would imply that's homeomorphic to the sphere. And the notion of the pick can be defined in any dimension, and this is the frame-dependent way of defining it. And later, a few years later, McCullough and McKenzie 1 also showed that the pick condition is preserved under connected sums, and they also derived some topological consequence. If it's pick, then the second Betti number has to be equal to 0 in the even dimensional case. And if it's a W pick, then the second Betti number is no more than 1. And if it's locally irreducible. And the Elena Fraser in 2003 showed that a compact manifold who has pick, then fundamental group cannot contain subgroup, I think, 2 copies of Z. And of course, these are all now, we have a complete understanding of the compact 4 manifold with pick condition, thanks to the works of Richard Hamilton and then Bing-Long Chen and Zhu and his colleagues. So in 1997, Hamilton initiated the surgery in the Ricci flow case in the 4 dimension. And of course, Karaman adapted and modified to make it work for 3-dimensional case. So, Hamilton essentially developed the pinching estimates in the 4-dimensional case, and then carried surgery. In surgery, there were some technical issues that couldn't quite justify, but then Bing-Long Chen and Jing, two friends, that they were able to carry through, extend the Karaman's work to 4-dimensional case with pick. So in this case, suppose there's no essential incompressible 3D space form, then they show that the such a pick 4 manifold is diffeomorphic to either copy of the S4 or its quotient P4 or S3 cross R, and then it's twisted product or connect some of those. So so there's some issue with the essential incompressible 3D space forms, and 15 years later, with another they were able to complete the whole thing, give a complete classification of 4 manifolds with a pick metric. So they diffeomorphic to S4, RP4, or finite quotient of S3 cross R, or their connect sums. So the pick condition remark is preserved by the Ricci flow. That's and also half pick, also Hamilton observed, is also preserved by Ricci flow. So half pick in that sense is natural for the Ricci flow, but that's preserved. And then how dimension, of course, is well known by Brander and Rick Shen and Nguyen independently, and they played an essential role in the solution of the Porter differentiable sphere theorem by Simon Brander and Rick Shen. Now, let me recall, say, finite time singularity models of the Ricci flow in general and compact manifolds are special types of these following 3 types. One is shrinking gradient Ricci solitons that they, for example, the neck pinch is one of them, and then steady gradient Ricci the degenerate shrinking degenerate neck pinch, or in general ancient solutions that exists for start from negative infinite time, and under certain conditions that they are possible singularity models for finite time singularity on compact manifolds. And what are gradient Ricci solitons? Those are extensions of Einstein metrics. So a Riemannian manifold is a gradient Ricci soliton if you have a potential function so that the Ricci tensor plus the Hessian of F is a multiple of the metric. And if it's shrinking, then that means that constant rho on the right-hand side, like positive Einstein case, is positive. We typically normalize it to be half. If it's steady, then it's the extension of Ricci flat, a la Bial manifold. And so essentially Ricci is a Hessian of a function. And of course, Einstein is a special case when F is a constant. And this notion was introduced by Hamilton in mid-1980s to understand singularity formations. So the significance, as I said, is these are actually give rise to self-similar solutions, because singularity, I learned from Zopin in also hyperbolic things that when you have from singularities, then in the fine scale, in the limit of dilations, they tends to have self-similar structure, and that is the case for the Ricci flow. That you have self-similar solutions given by scaling and diffeomorphisms. And they also model possible singularity formations. Shrinking study are type 1, type 2 singularity model defined by Hamilton. And the natural extension of Einstein, as we already saw, and these also have variational structures thanks to Paraman. And last but not least is they closely related to the powerful Liao-Hamilton differential Hanna estimates. So without Liao-Hamilton, even in 3-dimension or in 4-dimension, you don't have a tool for a priori estimates. So that really plays a significant role. So let me talk about classifications a little bit before we have to move further. So 2-dimension you completely understand. Shrinking or static case. Static case essentially is the non-flat what we support cigar solitron, and 2-dimensional compact shrinking one is either the sphere or it's the RP2. And in 3-dimension, the shrinking solitons, first compact ones are classified by IV thanks to Hamilton IV pinching. So that's a consequence. So it's only in all space forms quotient of S3. And Paraman was the first one to classify the non-compact case when the curvature is non-negative and bounded. So that's enough for the singularity coming out of the 3-manifold, compact 3-manifold. But then question is, turns out that you can remove the curvature assumptions based on some work of Ni and Warnock, Binglong, and Cheaping. We were able to remove the conditions, say basically any non-flat 3D shrinking solitron, it's either a space form or a quotient of S2 cross R, the standard ones. There's nothing, no else. And Binglong's work I mentioned plays a crucial role here. Now 3D it's more subtle because that's a delicate type of singularities, the type 2. So the first classification in 3D case for static solitron by Simon Brander, 2012, under the non-collapse condition. So it proved that they have to be brine solitron. So brine solitron is the rotational symmetric one defined on Rn. Has positive curvature operator or second curvature, essentially opens like a propylene. And that's the only rotational symmetric one on the Rn. And Hamilton conjectured that there should be one parameter family of 3-dimensional, but it's flat one that connects to the product of cigar cross R and then brine solitron. So they actually have an angle sort of from 0 to pi. So when the angle is 0, you've got the brine solitron rotational symmetric, and the angle is pi, it opens up and you get the product. And this turns out a very difficult, challenging problem. But in a series 3 papers, Eli has confirmed the Hamilton conjecture is true. One particular very impressive work is that she showed that every such non-compact collapser, one with positive curvature, must at least admit the S1 symmetry. And then using S1 symmetry, you can classify basically you have a family for each angle. So they are asymptotic to a sector, so you have a family. So 3-dimensional also, it's now understood. And so I have to say one of the really, all these works, 3-dimensional, use the Binglong-Chen's results, which says that's a kind of extension of the famous Hamilton IV pinching, which is a magic thing in 3-dimension. So Binglong showed that in JD 2009 paper says any 3D complete, particularly non-compact or compact ancient solution have non-negative sectional curvature. Of course, that's the same as non-negative curvature operator. So in particular, by combining with Hamilton's Strong maximum principle and the 2D classification, then you have either three-dimension is have to be strictly positively curved, or you have a product in those cases. And that also played a crucial role in our result I mentioned before for to remove Perelman's conditions. Now, as a consequence, then the Liao-Hamilton differential Harnack would be valid for all three-dimensional ancient, and that's again the essential role. And in four dimension, Binglong was able to prove that scalar curvature for ancient solutions in any dimension is non-active. So scalar curvature, which is very helpful, but scalar curvature is relatively weak, sort of. So we want to in four dimension. So four dimension, I would say, is in the shrinking case, it's understood. In the Einstein case, the work is done by Simon Brander. In general shrinking, which is solitone based on Hamilton's pinching estimates, Laney and his two former students were able to essentially using the Hamilton's estimates to sort of understand the shrinking piece. And so what I'm going to talk about is what about the static case or ancient solution or half-pick, which is we're really concerned about half-pick case. So first of all, this is a joint work with my former student, Junmin Xie, now at Rutgers University. The first result will be in four-dimensional case with W-pick and half W-pick. What's the geometry? We gained a little bit more understanding of geometry. And then the classification of partial classification of the four-dimensional static solitone with the W-pick. And then we have two more is shrinking and static with half-pick. We have some preliminary results. So the ancient solution, what we can prove is recall that we got this A and C matrix, and weakly W-pick means they both are two positive. And so what we show is you can, like in the Hamilton teaching case, this is weaker version, you gain some more positivity. So you start with the A and the C is weakly two positive, and then what it happens, it turns out is they actually are weakly positive definite. Not just the sum of these eigenvalues non-active, but the least eigenvalue of A and C are non-active. This turns out to be very useful. And using that, that was a year ago, and this is just posted about a week ago on arXiv, is we're using the top part, we were able to show that at least for ancient solutions, the W-pick, we raise on any manifold, the pick condition implies a scalar curvature only. But for ancient solutions, actually the pick implies positive reaching. So we gain a bit more control. And also because of this, then the entire curvature will be bounded by scalar curvature. So if scalar curvature goes to zero, then the curvature will have to go to zero, or scalar curvature is bounded, then the remaining curvature will be bounded. We have curvature bound and curvature asymptotics. So furthermore, if the ancient solution has pick, then the reach curvature will be strictly positive. So that at least tells us more about the volume and other things. And concerning on the static solid with W-pick, in 3D case, we already see the static case is much more subtle. So, so what we can show, first of all, this is easy consequence. Static case is because scalar curvature is bounded by 1, so we have bounded curvature. Now, so essentially, what we understand is the non-active case, non-positive case. So if we start with a four-dimensional complete non-compact and non-flat steady Ricci solitone and assume it's W-pick, then either it's pick, and of course then Ricci will be positive, or it has to be a Taylor-Ricci static solitone with positive holomorphic bisectional curvature, or otherwise it's a product. So this, in some sense, is like Berger's classification in terms of holomorphs. So still, of course, the difficulty issue is what happens with the pick. That remains open, and that way that will be very yeah, important to understand. And corollary is if you assume kappa non-collapse, so what you have is either pick or otherwise it's just the product of Franz or cross R. You know, and here we use Den and Du Xiaohua's work to that these Taylor ones have to be collapsed. So yeah. And now we move on to the really what we want to understand is half pick or half W pick. So if we assume the four manifold, its gradient static soliton is half pick, then either it's strictly half pick or W pick, then or otherwise it has to be Calabi-Yau, like Iguchi-Hansen, or hypotalar case, a local hypotalar. Or interesting case this happens. I remember Hamilton actually warned me about this interesting case, but that could be potentially trouble. Is they're Ricci flat, but they're self-dual. If it's anti-self-dual, then that's Calabi-Yau. But you also have this self-dual Ricci flat case that enters into the picture. And number case, then you have the Taylor case. And Taylor case, presumably those are collapsed if you use non-collapse condition, they will be done. And then you have the product case. So what really interesting is in this case, half pick case is to understand what is geometry classically half pick, and then the Calabi-Yau, of course, that's natural. So the Ricci flat and the self-dual case, I think needs more understanding. So finally, the one is the shrinking case. That plays the dominant role. The shrinking is the generic singularity in the Ricci flow. So this is the most essential case, as Benlo and the shipping would understand is. So in this case, if we assume half W pick in the shrinking case, then either it has to be picked, and that is the one the major question, and then the rest we understand completely. So either that's standard going on, and then the Taylor ones recently, thanks to the work of several people, Taylor ones are completely understand. So in remaining minute, I want to suggest the Binglong, not just the results, but his proof produced this very useful lemma. In the sense, if we have any dimension, you have complete ancient solution to the Ricci flow. And suppose we have Lipschitz function that typically comes like a least eigenvalue of a matrix, right? Least eigenvalue is that's Lipschitz method. So if you have a Lipschitz function and satisfy the differential OD inequality, the parabolic operator acting on U bigger than or equal to a small constant, the positive times U squared, then U becomes automatically non-negative and in the variance. So this turns out to be very useful. So I want to, so we certainly play the role. So now what are the open problems? I know time is up, and maybe I take one, probably still have 1 minute, right? So the one first open problem is essentially is to classify half pick. So in the picture we know only got 3 examples. The first two S4 and its quotient are actually picked. The only one really it's half pick is the CP2 or up to orientation, right? So if these are the only one, the conjecture is probably. However, what's the essential technical difficulty is we have to understand ABC. So if the P is to control the B, which is traceless Ricci part, but if you look at the evolution equation of B, that not only depends on A, but also on the C. So in a half-pick case, you got half the control. Either you have A, no A, or you got the C, but B depends on both. So somehow you need a bridge, say from one, how you got control, maybe A and C, that there's some relation that we don't know. So that's the technically major issue. And then the conjecture is it's extension of Binglong transfer result in 3 dimensions is if we assume it's picked, maybe there's a 4-dimensional Hamilton-Ivy Pynchon version saying the curvature operator has to be non-negative, or at least W pick 2 as well, we find the section of curvature non-active, and then Liao Hamilton would value. So that will be mostly enough for doing the or everything. So I want to say is under a much stronger assumption that for the uniphonetic, Troy and Lee from Kerda, they actually showed that actually the conjecture is true, but the uniform pick is it's strictly stronger conditions. And finally, we want to classify the steady solid with pick or even Riemann pick, so that 3-dimension took a long time and 4-dimension will probably take some additional time. But the Lai's work, he already construct a family of ones which is only pick but not some countercurrents. So hopefully there's some symmetries, and finally classify just for the Taylor geometry, classify the grading study Taylor sort with positive form bisectional curve, at least in complex dimension 2, and we have non-uniqueness several examples. So let me say thank Professor Yao again, and wish him many productive maths and make children wonderful again, much more wonderful, and we'll come back hopefully in 5 years. And so happy birthday, Professor Yao. Thank you.
Any questions?
Oh, you mean in the three-dimensional case?
Yeah.
Yeah, you have to essentially, in the you have to the infinity has something, because the infinity is like this, is look like a wedge across the cigar. So there's some kind of, so basically the infinity you have approximate S1 symmetry. So like in the Brazilian bracket case, is the infinity looks like S2 cross R, so you have full symmetry at the infinity. You want to make sure that inside has this. But in the non-clap case, that's technical, but in the clap case, that's even more technical. So essentially you have to also prove how the asymptotic S1 symmetry can carry the inside. So that's a subtle one. Yes. I can 100 pages. Yeah.
Well, there's an important question in general relativity, whether the station black hole is X-ray symmetric or not. That was proved by Hawking using real analyticity, which is far away from good. So this remaining uniqueness of black hole still needs to be proven. There's one of the major step was to prove that it's X-ray symmetric. After that, then the other argument take over.
That's right. H1 symmetry is
But this one is very important, so it is still not known. So physicists assume the black holes are unique. It's not unique, not clear to be proven at
so
all.
maybe the technique can have some.
Yeah.
Yeah, that
You can take a look, see whether you can do something.
Yeah, because many years ago, Rick Sean actually advised me that the some of the work actually related. So it's there's some.
Yeah. So for manifold, complex manifold are irreducible manifold. So I'm wondering if these rigid solitons can have some complex structures or simple structures.
That's excellent question. So so far, before they mentioned that we only have 4 all Taylor ones. So you have if you're optimistic, you may say, oh, maybe the rigid solitons has, maybe they're all complex or maybe all Taylor. We don't know, and there's some that's a big question. Yes, yeah, and but so far no, under some additional assumptions you can prove it, but otherwise it's wide open. Even say how do you get almost complex structure? That is an essential question. Yes.
Okay, any further questions? If not, let's thank the speaker again.
Thank you.